Okay guys, last video with respect to complex numbers, and really what I want to get at here is just we've been looking at what complex numbers are and operating with them, but why are we writing things as complex numbers in the first place? And so ultimately what it comes down to is we're going to be looking for zeros of polynomial functions. And so in these examples here, you're going to notice it says solve the quadratic functions for their zeros, use a graph to help support your results. So when we're looking for zeros, let's just acknowledge first of all that what we're looking for, at least graphically, are the x-intercepts. And so we're setting y equal to 0 and we're working on solving for x. And so we're going to do this algebraically, but notice one thing I said was use a graph to support your results. Well, I want you to consider that if we put in y equals x minus 2 quantity squared plus 9, we graph it, we should get a quadratic family of functions graph, and you see it kind of up here that is shifted right 2 and up 9. So first things first, before I'm even solving this, what I want you to recognize is that nowhere does this have an x-intercept. And so that being said, what it really indicates is that when we try to solve this algebraically, we're not going to get real zeros. The x-axis only contains real zeros. So graphically, we already understand we're going to get imaginary results. Let's look at how this plays into maybe solving a polynomial equation. So if I were to subtract 9 from both sides of this quadratic equation, we get negative 9 equals x minus 2 quantity squared. And from here, we can go ahead and take our square root. Now, what do we know about the square roots of negatives? We know that they're imaginary and that we can rewrite them as a positive on the inside, but that we have to put an I out in front. And so what we end up with here on the left-hand side is the square root of 9, which I'm finally going to write the plus or minus part here. Plus or minus 3i equals x minus 2. And as we add 2 to both sides, we're going to get x equals 2 plus or minus 3i. And so you can see that we got two solutions here, and each one is a complex number. Not only that, we got something else really cool to happen. We started to see that complex number answers, they occur in conjugate pairs, but they only could because you only get complex numbers when we're taking square roots and negatives, and if you're taking a square root, then there had to be a plus or minus involved on the I part of this. So complex numbers or complex zeros occur in conjugate pairs. But you can see that it would be necessary for us to understand a little bit about complex numbers to be able to interpret this result right here. So let's take a look at letter B here. And this says g of x equals x squared plus 6x plus 10. A couple of things I want you to notice. The first one is just that this is not in vertex form. This is in what we refer to as standard form. So with respect to the graph, I'm going to go ahead and make a quick graph here. But you see that it kind of misses the x-axis here. It looks like it's heading for a 0, but nope, it decided to change its mind and turn around. So with respect to finding the zeros of this, I suppose I would set it equal to 0 first, and then I would try to get x by itself. Now the thing here is, it's hard to get x by itself. We have x's to the second and x's to the first. So our choices so far would be, 1, to try to factor this. The unfortunate thing for us is that it does not factor. There are no factors of positive 10 that add up to be a positive 6. So our alternatives at this point are going to be either completing the square or using the quadratic formula. In this particular case, I want to make sure that we're good with this quadratic formula. So I'm going to write that up here. We would say the solutions to this equation, where I've got a standard form thing equal to 0, would be this right here, both of these x values. And so in this particular case, A, B, and C are 1, positive 6, and positive 10 respectively. Let's go ahead and then say that our zeros then have to be negative b, so negative 6, plus or minus b squared, so we're going to get 6 squared, minus 4 times a, which is 1, times c, which is 10, and this is all going to be over 2 times a, which is 1. So already we've found our zeros here. We just need to clean this up a little bit. So things that we tend to do. We tend to go ahead and take care of this first term out here in the denominator right off the bat. 2 times 1 is 2. Now this is all plus or minus what? Well, on the inside of here, 36 is what we get when we square our 6. And I look at these three terms here as negative 4 times a 1 times a 10. I look at it as a negative times a positive times a positive. So I know I'm going to get a negative, and I know 4 times 1 times 10 is 40. So I don't know if you see it yet, why we're not going to get real zeros here. Let's simplify it a step further here. There it is right there. The fact that we got a negative inside of our radical. So simplifying this using the properties of imaginaries and complex numbers, we're going to rewrite this as negative 6 plus or minus I times the square root of positive 4 all over 2. Remember, we can take the I out in front and make what's inside here positive, but you might see that that actually leads us to be able to simplify this further. And so we get negative 6 plus or minus 2I all over 2. And because the top and the bottom, every term shares a common factor here, we can divide each of these by a 2, which gives us a 1, and a negative 3. So we get negative 3 plus or minus I would be our two complex number solutions here. So you can see that it's going to be completely necessary for us to be familiar with complex numbers, how to write them in standard form, and how to work with square roots of negatives and i's in order to find our complex number solutions to, say, quadratic functions that don't have real zeros. Cheers.